Okay, let's do some notes on function transformations. This is a really important topic, something that's going to come up a lot throughout the rest of this class. So some things to keep in mind. When we talk about functions, we're referring to, y as a function of x, right? You plug in x, you get out y. So an important piece of vocab is the parent function. So when I talk about a parent function, what I'm referring to is the most basic form. So the most basic form of some certain type of function, of a certain type of function. So for example, if we talk about quadratics, right? If we talk about quadratics, the most basic quadratic I can write would be just y equals x squared. So anything else I do to manipulate that would fall in that function family of quadratics, okay, where x squared is the parent function. All right. So when we do transformations, we're talking about taking some parent function, doing a bunch of stuff to it, and seeing how that affects the graph. Now, we did that pear deck activity where we looked at a bunch of different types of functions, and they all had this kind of similar format. We saw how changing the sliders for a, h, and k transformed those functions. Right? So we're going to be doing a little bit more with that today. Okay. A translation. So that's something that you definitely talked about in your geometry class, wherein you were doing, transformations of different shapes. So a translation, what you can do is, imagine you have the graph of your function is a magnet. It's sitting on your fridge. Okay, your fridge is the coordinate plane. You can slide that around, right? You can move it up, you can slide it down, you can slide it to the left and right, but that's not going to change the size or the general shape of the function. It's just going to be shifting it in some combination of up, down, left, and right. So that's all we're doing. So, we're just either doing a vertical shift or a horizontal shift. Okay? So think about a vertical shift. If you are moving up and down, what you're doing is you're moving along the y-axis, right? You're moving somewhere along the y-axis. So if you're shifting your function vertically, you're changing the, primarily you're thinking about changing the y values. So for something like f of x, that means we are adding or subtracting some value of k, okay, some constant onto the end of that. If we add something to the end, we're going to move it up. If we subtract something, we'll move it down. So we could take a look at Desmos. I have this example here of y equals x squared. Right? If we took that, we'll think of that as our function, f of x. Right? If we added 2 to that, plus 2, all it does is it shifts it up 2. Right? If you want to see both at the same time, we can say f of x plus 2. Right? We're just moving that function up 2. If we want to move it down 2, minus 2. Right? We're just shifting it up or down. It doesn't change the shape, just a vertical shift. Okay? For a horizontal shift, right, the x-axis is the horizontal axis. Okay? The x-axis is the horizontal axis. And so if we're shifting our graph horizontally, we're thinking about changing the x or the input values, right? That's actually inside of the function. So we would be adding or subtracting some value. And I'm going to use h, some value to x, and we'll see how that affects the graph. Okay, so let's go back to that Desmos graph. Okay, so I have my x squared. Now I'm going to see what happens when I add 3 to x. So I'm going to add 3. Okay, which direction did it shift? Here's our parent function. Here's our transformation. Another way that you could write this, if you think about function composition, x plus 3 all squared, right? We moved 3 units to the left. Okay, we moved 3 units to the left. And that's kind of counterintuitive, right? Because we were doing plus 3. So something to keep in mind here for a horizontal shift is it's going to shift in the opposite direction of whatever you just added. Okay, so if you're doing plus h, you're going to move to the left. If you're subtracting something, you're actually going to move to the right. I know it's a little funky, but with a little bit of practice, you'll definitely get the hang of it. Okay, so let's look at a couple examples here. So we have y equals x squared. Let's think about using these rules, how we could describe the translation that's going to happen. Okay, we want to try and do this without looking at the graph. So first I see x minus 3 in parentheses. So whatever's going on in parentheses, that's going to be some change to whatever I'm plugging in, right? In other words, a change to the x value. So that's going to represent my horizontal shift. This is minus 3, so I'm going to be moving to the right. Okay. Minus 5 on the end is shifting my graph down 5. Let's take a look at the graph and just verify. Okay, so there's x squared. So we do x minus 3 squared. So that moved us to the right 3. Minus 5 shifts us down 5. And if we actually compare the bottoms of these parabolas, you know, it's really easy to see the translation. We went to the right 3 and we went down 5. All right, next example. So now we're given a function, square root x, and we want to think about what it would look like, or what the new function would look like if it had a vertical shift of up 5 and a horizontal shift left 17. Okay. So I'm going to use my kind of function notation first. So my horizontal shift left 17 means I'm going to add 17. And then up 5, add 5 outside of the parentheses. So what would that look like in the square root function? We'd have the square root of whatever's inside the parentheses, so x plus 17. And then outside the radical, we're going to have plus 5. Let's check out this graph. So we have the square root of x. Let's zoom out a little bit so we can see everything. Okay. Now we'll do x plus 17 under the radical plus 5. So if you notice the plus 17, there's our shift left 17. Adding 5 shifts us up 5. Okay, moving on. Let's talk scale. So when I'm talking about scale changes, changing the scale of the function, scaling it up, scaling it down, we're looking at, you know, some form of stretching or compression. Some form of stretching or compressing the graph. We might use the word shrink instead of compress here, but you'll see them kind of used interchangeably. So a vertical shrink, now remember, we're dealing with, you know, y as a function of x, right? So if I'm thinking about a vertical shrink, what I'm doing is I'm multiplying by my y value. So I'm multiplying some constant times f of x. Whereas with a horizontal shrink, right, that multiplication is happening inside the parentheses. Okay? So vertical shrink happening outside the parentheses, horizontal shrink is happening inside the parentheses. Stretch or shrink, I'm sorry. We have a word for A. We call this the scale factor. And when our scale factor is in between 0 and 1, we always think of our scale factor as a positive number, because when it's negative, then we start dealing with reflections, which we'll get to in a moment. So when A is between 0 and 1, that's called a shrink. When A is bigger than 1, you're looking at some sort of stretching. Okay? And we'll take a look at what that looks like with the graph of x squared. Okay, so we have x squared. If I were to multiply this by 2, so 2 times f of x, notice that it stretches the graph, right? So it's like it's pulling it up, and it's getting more narrow, right? It's getting more narrow. This is the same as if I had done 2 times x squared. Exact same. Okay? Now let's see what happens if I multiply by 2 inside the parentheses, so f of 2x. If we notice, that stretch is even more exaggerated, and that's because, you know, if we're doing f of 2x for a function like x squared, oops, what that's doing is I'm squaring 2x. So I'm looking at 4x squared, right? So it's stretching by even more. Okay. If we multiplied by something in between 0 and 1, let's multiply by 1/2. It's going to make the graph a little bit wider, smush it down a little bit. Okay? That's why I like the term compression as opposed to shrink. So in this example, we have a parent function of y equals x squared, and we just want to describe the scale. So we're just looking at what's being multiplied here. So I'm multiplying by 4 on the outside, so that would be a vertical stretch. Okay, we know it's a stretch because 4 is bigger than 1. Vertical stretch by a scale factor of 4. Oops. Vertical stretch by a scale factor of 4. And for the second part, we see we're multiplying by 2 on the inside of the parentheses, so that's going to be a horizontal stretch. A horizontal stretch by a scale factor of 2. Okay. All right. For the next example, our parent function is x cubed. So if I'm shifting vertically, remember that's multiplying outside the parentheses. So, oh, I'm sorry, vertical shift down. So we're going to be going down 5, right? And a horizontal shrink, so inside the parentheses, of 1/3. So in other words, we have f of 1/3 x, and then we're subtracting 5. So if we write that in terms of x cubed, whatever goes in the parentheses we're cubing, so 1/3 x cubed, and then minus 5. Let's see, now we have a horizontal shift to the right of 2. Vertical shift, so we're going right 2, going up 3, and a vertical stretch by a factor of 4. Okay? So let's think about our horizontal shift. That's going to happen inside the parentheses. We are going right 2. So that means I'm going to subtract 2. So I have minus 2. Inside, up 3. And a vertical stretch by a factor of 4. So I'm going to multiply this function by 4. So here's what that looks like. We're going to do 4 parentheses x minus 2 cubed, because that's our parent function, plus 3. Okay, and I definitely suggest you try graphing these and graph the original and you know, see how they change. See if you can really spot the changes step by step. Okay, so kind of the last type of transformation we want to talk about is the reflection. So, you know, that's where we are flipping our graph over some axis. Okay, and when we flip, we're multiplying by a negative, right? So if we flip about the x-axis, think about which direction you're flipping. So this is, you're flipping vertically, right? If you're flipping over the x-axis, right? You're taking your graph or your shape and you're flipping it over the x-axis. So when we do this, we're actually multiplying on the outside, multiplying by -1 on the outside. Okay. Flipping over the y-axis, that's a horizontal flip. In order to flip over our vertical line, we're flipping horizontally. So I would be multiplying by a negative inside of my function. Okay. Now there are some functions where these two things are the same. Okay, there's some functions where multiplying by a negative outside is the same as multiplying by a negative inside, and that's something we can spend a lot of time on later. But let's look at some examples. You know, I mean, an easy one to look at is x squared versus negative x squared. Right? That's a flip over the x-axis. That's a vertical flip. So if I'm looking at, let's see, I have y equals x squared. I just want to think about the reflection. So you want to think, you know, where am I multiplying by a negative? So here I'm multiplying by a negative outside. Oops. Here I'm multiplying by a negative outside of the parentheses. So that means that this function should be flipping over the x-axis. So we should be reflecting over the x-axis. And we'll graph these in a minute to verify. On the other example, take a look at this. There's no negative outside the parentheses, but inside you have things switched around. This is 4 minus x. Well, that would be the same as saying negative x plus 4. So we're multiplying the x inside the parentheses by a negative. That means we're reflecting over the y-axis. Let's take a look at these graphs. So let's see in the first one. Okay, we're going to graph y equals x squared just so we can keep an eye on the parent function. Now let's look. Negative 4 we have x minus 3, okay. Squared. See how it's flipping? And we got some stretching going on. Minus 5, and we're shifting down. Whereas with the other one, I have 2, 4 minus x squared. Yep, and then what, plus 3? Minus 5 again, sorry. Minus 5. So you can't really see a flip around the y-axis because a parabola is symmetrical about the y-axis. All right, let's do one more example. So we have a parent function of, this time we're dealing with absolute value x. So we need a vertical shift up 1. So we want to go up 1. And we want to reflect about the x-axis. So that would be like -1 times our function, and then plus 1. Or -1 times absolute value x plus 1. Okay. Horizontal shift left 2. So I'm going to go left 2. Vertical shrink by a factor of 5. And reflect about the y-axis. Okay, so our horizontal shift. So if I'm going left 2, I'm adding 2 to my x. If I am reflecting about the y-axis, I need to put a negative in front of x. And let's think about a vertical shrink by a factor of 5. So if we're shrinking by a factor of 5, right? Think of shrinking as dividing. That's like dividing by 5, right? Dividing something by 5 is the same as multiplying something by 1/5. So we're going to put a 1/5 outside of our function. So this would be 1/5 times the absolute value. Now you could write this as -x plus 2, or you could write this as 2 minus x. Either way would be fine. 2 minus x. And you're done.